Hello, welcome to our second webinar of 2020. And what we're going to be talking about today is the recently released version of ISO 6336 2019. So what we're going to be doing really here is a comparison between the 2006 version, which is currently the default in MASTA, and the new 2019, which has been implemented into the software. So joining me today is Beidou Al, who amongst other things is a gear specialist here at SMT. So he has a breadth of knowledge about this topic. And as always, if you have any questions at any point, please do put them in the questions panel. We will either address them as we're going along, or we'll answer the questions at the end, or either all together in the chat, or we'll just answer them individually. So to start off with, a little bit of information about ISO 6336 2019. So it was released in December 2019 and has been implemented in MASTA since version 10.03, which was released on the 31st of January. Now the selection of this standard, so the 2019 version, is done within the settings menu in MASTA. By default, MASTA will still use the 2006 version, so you don't need to worry about that. Changing it to 2019 is something that you have to specifically do. So we've done this as we're aware that the industry won't adapt it straight away. So just be aware that within the settings menu, you have to specifically activate the 2019 rating method. So what we're actually doing in this presentation, in this webinar, is showing a summary of the significant changes between the old and the new version. And we're going to demonstrate their effects on some example project designs. So the results we're going to show you are from actual projects. They're very much anonymized, but it should give you a realistic representation, so more than just using our simple example models. Okay, so what we have on the screen here is just a very brief summary of some general results, and we'll go into certain bits of this in more detail. And this kind of format is how we'll see quite a lot of the results in this presentation. So we have an equal line going through the center of the chart, and then on the X and Y axes, we're looking at whatever result in the 2006 and the 2019 versions. So the equal line going down the center is what we're aiming for. And we've also put on some of the charts a 15% deviation line as well, just to see if you're in a particular range of results. And zooming in a little to a more condensed safety factor range in here, just to show, what we can generally see here is that there are some significant deviations between the two versions, and we'll focus on some of these results as we go through this presentation. But you can also see that the main difference, the main change in the results comes in terms of bending safety factor. Contact generally is quite similar, so bending is what we'll generally be focusing on. So to start off, we'll look at some of the changes in ISO 6336 section 1. And what this mainly focuses on is the dynamic factor, so KV for low load. So just as a bit of an overview as to what this factor actually is and what it relates to, it accounts for internally generated tooth loads induced by non-uniform meshing action. So this is a number of different things. For example, it could be the inclusion of transmission error, overload effects, pitch errors, and profile errors. Now, the main differences here is the fact that this is now clipped in 2019. So in the 2019 version of ISO 6336, if operating outside the resonance condition and KV is greater than 2, then KV is clipped at 2, and then we give a warning within the software as well. In comparison to 2006, KV is not clipped, and values less than 1 can also be calculated.
This is the dynamic factor is affecting both bending safety factor and contact safety factor simultaneously, as it's a multiplier to transmitted force. We will actually have a look at a brief example which you would be able to see its effects. Also, we have implemented an option for this to be used by previous releases of ISO 6336 if you would like to compare your results with this factor. So here we see a example design which comes from our engineering department, and this is from a high-speed industrial gearbox. During its startup operation, it actually goes through various different stages of the resonance condition. So you can see some of the safety factors calculated by the new version of ISO 6336 is significantly higher compared to the ones calculated by its previous version. This is due to this dynamic factor clipping outside its resonance range. And at the bottom chart, you can actually see in a log-log scale the dynamic factor being clipped to 2 and not clipped within its main resonance range.
Okay, so main changes to part 2 of the standard. This is mainly relating to contact factors and work hardening factor. So for the contact factors, so ZB and ZD, these factors are applied to the nominal calculated value for contact stress. And what these essentially do is transform the contact stress at the pitch point of spur gears to the contact stress of the inner point B for the pinion or D for the wheel. And then it's the highest of these two that is selected. So what we have in here, one of the changes is a new factor that's been introduced, which is FZCA. And that's introduced to take into account the flank modification effects on contact stresses. So there's 3 options in here which have been put into MASTA as well. We have suitable, we have based on practical experience, and we have none. So the default value we have in the software is 1, which is suitable, which equates to a value of 1 for the factor. And what we would generally consider is that if you're using MASTA as a piece of software, then you wouldn't want to really change that value. Then just a bit of an overview as to what the other options would do, which is shown on the table on the left. So the based on practical experience will increase the factor slightly from 1 to 1.07, and then none will increase it again to 1.2.
The default factor of FZCA, as Sam mentioned, is 1, which assumes the microgeometry is defined and designed using MASTA. And both ZB and ZD, the contact factors, are identical to previous version for this given default case. If the FZCA is different, both parts B and C would result in different values. But again, if the microgeometry of your gears are designed within MASTA, this shouldn't actually affect you. The next change in part 2 is relating to work hardening factors. So the new standard actually has a new section, which is an addition to 2 other ones, which used to cover true hardened gears. The work hardening factor is increased capacity of the gear flank when it's in mesh with a significantly higher higher hardness gear due to the work hardening effects. This new section covers the ductile iron gear, which is in mesh with a surface hardened steel. We currently do not have an example for this, but if you are interested in an example, we would be happy to pass literature to you. So please let us know.
Okay, so changes for section 3. Again, it's focused on two major areas, and this is helix angle factor and form factor. So to briefly explain what these two factors are, if you're not aware, so helix angle factor is in there to compensate for the changes in bending moment intensity at the tooth root of helical gears due to the oblique lines of contact, and this is when compared to spur gears.
The general impression in testing and within the ISO TC60 committee, which is responsible from these standards, is the bending safety factors were too high using the previous versions of ISO 6336 for helical gears. So the risk of failure was actually greater than the predicted with the previous versions. The new standard incorporates 1/, cos beta cubed factor, which changes the way the helix angle factor behaves to a great extent. On the left-hand chart, you can see a screen capture from ISO 6336 2006 version. And on the right-hand side, you can actually see the new version. In the old version, the values used to be always less than 1. And in the new version, the significant amount of the values are actually greater than 1. The effect of this would be making your safety factor worse, but it will also interact with a form factor, which we will be discussing in later slides.
Okay, so the other thing in section 3 that's changed is the form factor. So this accounts for the influence on nominal tooth root stress of the tooth form with load applied at the outer point of a single pair tooth contact. So the main thing we're considering here is that there is a new factor, F epsilon, which is introduced to consider the effects of contact ratio on the actual form factor value.
One of the things we should also mention, and we will cover later on, there is a new method for calculating the bending geometry for shaped gears, and again it will be actually discussed a few slides later. For now, we will be focusing on this new factor, F epsilon. This new factor is there to actually capture the influence of the load distribution in the teeth. So it actually covers different values for different contact ratios. As you can see from the chart on the right-hand side, there are a few main areas, and there is a step within it. The biggest value of the step occurs for a helical gear, for a spur gear, at the transition between contact ratio of 2. The F epsilon value would be equal to 1, which would mean the values would be identical for the previous versions for spur gears with contact ratio of 2. If the contact ratio increases beyond 2, then the value of it will decrease to 0.7. This would mean for a spur gear with a contact ratio of 2, we would see an increase in our bending safety factor, which is equal to 1/0.7, which is approximately 42%. One of the things I would like to focus on here is we should actually be careful with this change, because if we have a spur gear and we think we are just over contact ratio of 2 and we add a tip relief, we might suddenly actually have a contact ratio less than 2, which might not equate to this difference. Helical gears also have different factors. Again, the values of F epsilon would be actually contributing to increase your safety factors in general, and it would be balanced a little bit with the helix angle factor.
So what we're going to look at on the next few slides is just the comparison of a few different gear sets from different models, which go through different conditions, or these different equations that we've got listed on the screen now. So this is the format that we will be looking at generally. So just to go through this very briefly, the plot at the top will be to do with the direct comparison of safety factors, normally bending, but may include contact as well, between the 2006 and 2019 versions. And then at the bottom, the chart at the bottom on these next few slides will be showing us how the form factor and the helix angle factor have changed for that particular gear set. So just to reiterate, these are from actual units. These aren't from our simple sample models, which don't show you that much information. They've of course been anonymized, but these should give you some representative results as to how the resulting factors and resulting safety factors have changed between models. So over on the right-hand side as well, we do have the plot that Bedu showed on the last screen, and it does show you where the current gear set actually sits on that 3D plot. So it kind of gives you a representation as to what we're looking at here.
This first slide captures a spur gear with contact ratio less than 2, as we discussed a little bit in the previous slide. This is a case which we wouldn't actually expect any change. As you can see, the bending safety factor is on our perfect fit between both cases, showing that the safety factor didn't change. Also, this corresponds to both form factor and helix angle factor. They are both equal to the previous values. So this is probably a case which is most affected by the new standard. We are talking about a spur gear with a contact ratio greater than 2. So F epsilon value that you would get is 0.7, and you will be just beyond this step that I discussed. We are talking about spur gear, so the helix angle factor is equal to 1. And the form factor calculated will be 70% of the previous value, which results into 33% increase in our safety factor. So the next one that we would look at is a helical gear with overlap ratio less than 1 with virtual contact ratio less than 2. This actually plays in one of the equations which has the highest slope, and you wouldn't be able to predict if the values are actually going to increase or decrease for a safety factor. The example we have actually given here it actually decreases, but we will actually later on show you the values affecting in both directions for a different helical gear. So here you can actually see the helix angle factor increased than its previous value due to 1/cos beta cubed added into the equation, and our form factors actually decreased by a certain amount. And the overall balance of these lead to safety factor decreasing. So this is another helical gear, again with overlap ratio less than 2, but now we are looking for a virtual contact ratio greater than or equal to 2. For most of the cases, the banding safety factor is quite close to its previous value, with some possible decrease in it. Here we are actually seeing a helix angle factor increased, again with the same factor as previously discussed, and form factor has been decreased due, or as in on the chart, the value of the form factor will be slightly less than 0.7. The last possible calculation method for F epsilon will be for helical gears calculated for overlap ratio greater than 2. Here the same thing applies for the helix angle factor as discussed before, and with relevance to the form factor, we are on a large descending slope with the virtual contact ratio. The safety factor here actually increased, but the next slide will actually show some interesting behavior. So again, we are actually on the same slope, and we are looking for a complete design, which we would look at later on in slightly more in detail. Here we have 3 different gear sets, and they are all calculated according to equation 14, which is helical overlap ratio greater than 1. But we actually see a different behavior for each of these gear sets, which is showing the trend of behavior between the form factor and helix angle factor. Previously we a little bit discussed about the change to the tooth root geometry due to shaped gears as well. The previous standard 1996 and 2006 versions used to have an approximation for fillet root radius. And this would apply to pinion type cutter, which is a shaper tool, or similar to the shaping tool. But this approximation was not very accurate for very tough reasons. The new standard 2019 version actually takes calculation method from VDI 2737, which is a general calculation method for internal gears, and it incorporates the calculation for normal root chord, radius of root fillet, and bending moment arm into ISO 6336. So as a result of this, these factors would significantly change as we are actually using the actual root geometry defined by this shaper tool. One thing we would like to iterate here would be if you have an external gear defined by a shaper tool, this calculation applies to it. However, the examples that we are going to cover here are going to be only for internal gears. For the first example, bending moment arm decrease, this actually a positive effect for our bending safety factor, and our tooth root chord actually decreased, which is a negative factor, and the root fillet radius increased by 50%. If we look at our example 2, we see similar trends for bending moment arm and tooth root chord. However, the calculated root fillet radius actually decreased in this case.
Okay, so what we're going to look at now is, instead of looking at some individual gear set results, as we saw there, which is quite small scale, we're going to look at some entire gearbox scale results. So this is more looking at what distribution you might expect if you're looking at a whole gear set rather than just focusing on one thing, and gives you a bit more of a rounded understanding of what might influence other things. The format we're going to use for this is fairly standard, the same as we used in the previous. We're going to have the bending safety factor comparison between ISO 6336 2006 on the x-axis and 2019 on the y-axis. And on the right-hand side, we'll look at the contact safety factor with the same thing. The main thing we're looking at is the line down the middle, which is the equals line. If it's exactly on that line, then it's an equal value between the two standards. And obviously, the further we deviate from that central line, the greater difference there is between those values, and we'll probably end up discussing those individual cases.
So the first example that we have is a 12-speed gearbox, and this is mainly a Spur gear unit, and probably we can actually start with the easiest comparison. On the right-hand side, you actually see contact safety factor didn't actually change at all for this given case. If we actually look at to bending safety factor comparison on the left-hand side, we can actually see one of the gear sets, or one of the gears actually didn't change at all, and some of the others actually changed rather significantly. The biggest change, which is actually circled, is due to Spur gears with contact ratio greater than 2, which would get F epsilon of 0.7, which would show an increase in safety factors about 43%. And again, the other ones would be helical gears. The one on the identical line is a Spur gear with contact ratio less than 2, and the other gears which show slight increase less than the other Spur gears are helical gears, which show slight increase onto their safety factors. This is another 12-speed gearbox. However, it actually has a different layout. Here, the gear which we would like to stress on is the ring gear of a reduction section of the gearbox, and this planetary set is a Spur, so you can actually see similar colored on the identical comparison line. So those are sun and planetary gears, and ring gears circled actually show approximately 14–15% reduction in their safety factors. In relation to the contact safety factor, again, the results are identical for both standards. So here we would actually look at what actually caused this change. As previously previously this is due to the calculation method for our ring gear rating geometry. Previously we were actually approximating what would a bending moment arm and root cord would be. However, in the new standard, we have a more accurate way to calculate these. Also, probably it was worth mentioning that if you were using cutters in design mode or the manufacturing mode in MASTA, these values are actually calculated based on the geometry rather than using the equations in the standard. So the next example we have is a 6-speed automotive gearbox, and here it's predominantly helical, and we actually see safety factors both increasing and decreasing due to form factor and helix angle factor, as we previously discussed. The biggest reduction that we see here is due to helical gear with overlap ratio less than 1 and virtual contact ratio less than 2. The general trend is similar to that we actually discussed for individual sets before. This Automotive E-axle project, which has been done at SMT. All the gears used in this gearbox are helical, and they have overlap ratio greater than 1, and all of them actually show an increase in safety factor. The next example is a hybrid gearbox from our automotive application, again, we actually had a look at this, the bending safety factor part a little bit before. Here, they're all helical overlap ratio greater than 1, but you actually see a difference trends in safety factors for each gear set dependent on the helix angle and the contact ratios. This high-speed marine application, and it actually has a startup condition which actually gets into a resonance region and out of it again. This would mean we would be affected by the clipping, which was introduced in 2019. As mentioned before, this would actually affect both of our bending and contact safety factors simultaneously, and some of the trends you actually look at might not be expected as some of the safety factors increase quite significantly. If we switch on this clipping for ISO 6336 2006 version, the lines would actually become more linear. There will be a slight variation due to quite low torques and them being different in to run analysis, but this slide would actually show the clipping effects in the dynamic factor. So the non-clipped region would actually show a trend which should be one-to-one between the same versions, and there will be a clipped region which is outside the main resonance range. So we have discussed the changes in the new version of ISO 6336 and referenced some engineering projects which relate into how the behavior actually changed. The largest negative impact that we actually observed in these examples were for internal gears due to introduction of new calculation methods for gears generated by shaper cutters. So this has a rather large impact on the rating results. One thing you might want to consider is if you actually have external shaper cut gears, you can actually switch to using pinion type cutter and see if the root geometry would be different for those applications. On the other hand, the largest percentage change that we observed was due to clipping of dynamic factor. This only applies outside the main resonance range. And probably it would be worth thinking slightly more beyond the safety factor, even though the safety factors for these cases which are affected were reasonably high. The effect of them on the overall damage on the gearbox might not be. So we would need to actually take into account amount of cycles which each load case correspond to in that case. The general differences that we observe are in the bending safety factor, and this is both due to changes in form factor and a helix angle factor.
Okay, so in terms of the technical content of the webinar, that's about it for today. So thank you very much for your attention. We do have a couple of questions come in. We'll probably answer those after the webinar has ended in the text chat. Before we wrap up here, though, I do just want to point out the next webinar that we have running. So I think it's about a month from now. So on the 7th of April, we are running one which is discussing the different programming languages that we can use to actually do scripting within MASTA. So if you are not tied to a particular programming language, you want to know which one you want to proceed with, please do join us for that. If registration isn't open right now, it will be very, very soon. So I encourage you to sign up for that as soon as you can. So thank you very much for attending. I hope you found it very, very useful, and we will speak to you again next time. Again, we will reply to any questions in the text panel in a few minutes. Thank you very much and goodbye.